Good evening, everybody. Welcome to the new format for this particular meeting. Like Steve said, we're going to do something a little different tonight. We're going to watch a very entertaining and insightful video from Gentry Lee at JPL. And then the idea is that we're going to then interpret what we heard through the eyes and ears and lips of our panelists, who will be Dan, Dave, and Steve. And then I'll moderate by asking a couple of questions, and then we're going to entertain other questions. Logistics, if you have a question you'd like to ask, you can put it in the chat if you want, or since it's a pretty small group tonight, I suggest you just wait after you watch the video and start the panel discussion. You will be able to ask your question then. With that, I'm going to start the video. Just give me a second to share my screen. Make sure everything's set. Okay. And the video, like it says here, is about 39 minutes long.
Okay. We'll check the mic first, make sure it's working. You can all hear me fine? Yep. All right. What are we going to do today? We're going to have fun, and we're going to learn something. I'm going to share some points of view. You'll agree with them, disagree with them, whatever. I want you to at least think about them. Now, why am I here, and what am I going to do that's different than when I was up here in June of 2005? In June of 2005, I gave a talk on systems engineering and what attributes you had to have in order to be a good systems engineer. But that entire talk was aimed at how, okay? And it assumed that something was already defined to be engineered. Okay. Now, there are two questions that come before that. If what you do is you back off far enough from all the things that we do, the flow of primary questions, if you allow me to invoke that sort of phrase, goes like this. Why, what, and then how? Okay? So what I'm going to talk about is what is the system engineer's role when the dominant questions are why and what. And because everybody likes lists from Letterman to Lee, okay, or however you want to do it, I'm going to eventually give you the top 10 attributes of a system engineer who plays in this why, what field more than the how field. Now, somebody said, please don't use any of the same attributes you used for the other guy. Okay, because that, you know, people like to have disjoint sets. I will say to start with, however, that you know, of course, you can't do this job if you don't have intellectual curiosity. And Jeff Leising pointed out to me, you know, it may be obvious to everybody, but you need to say it. This job of being a system engineer in the what and why field is more like being an architect than it is like being an engineer. And it's important that you realize that. I tried this on my sons just to see whether or not they understood the difference. And they said, sure, Dad, we understand. The architect designs the building and the engineer builds it. And I said, okay, that's close enough, and that's what we're talking about. So what we're going to do now is we're going to have a brief step back, because we're going to go to the first attribute, and I'm going to set the context for this entire discussion. Here we come. We're doing the top 10. Number 1. Science smart. Okay, systems engineers, you can get away with understanding little or nothing about the science you're implementing if you're in the how phase. You cannot if you're in the why and what phase. Your best friend should be a book on geology or planetary science. You should read the journals. You should understand what it is the scientists are trying to achieve. Imagine the evolution of the why questions. You could be out of date, for example, because you only know the questions that were asked about Enceladus 4 years ago. Hello? There's not a whole set of different questions that are being asked right now. Now, I had somebody limp into my office, and they were very upset with me. They said, you expect everybody to be able to do everything. I said, no, I don't expect them to. I just think they should aspire to. And then he went on and said, I don't know anything about geology. I never took a course in geology. How am I supposed to talk to Dr. So-and-so, who's a PhD at Washington University of St. Louis, about geology? I said, what you do is you simply say, I need to understand, first and foremost, what are the questions? Okay? Now that sounds very, very simple. And yet, I find that many people, when I ask them, they say, I have some mission such and such, and this is what I've designed it to do. I said, what are the questions that this mission is designed to answer? What do you mean? No, I said, there's had to be somebody saying there's issues that I don't know the answer to, like maybe what's the core structure of the moon, or what are the things that are contained in the plumes that are coming off of Enceladus, or something like that in the beginning. Somebody had to tie that to the origin and destiny of the solar system and everything else. If you don't know that, okay, you are handicapped in the early, in the beginning part, because it is a merger of science and engineering, and it is unfair for you working at the Jet Propulsion Laboratory to expect the scientists to come more than halfway to you. That's not their job. It is your job to go more than halfway to them. You have to understand the what, why, and then you have to get to the what. How does this all work? What is our business about? It's a simple flow. What are the questions? Which comes from, what are the hypotheses? How do I answer the questions? Okay? You answer the questions by taking observations. Now, somebody says, well, there's other ways to answer the questions. I said, yeah, you could go, I said, that's not what we do here. We try to have specific ways to answer the questions, which then maps into measurements that need to be taken, instruments that need to be designed, and then it gets more quantitative all the way down there. But this front-end process of being science smart means you have to understand what it is they're trying to achieve. Let me give you an example, or several. Right now we're talking in the future about a New Frontiers missions, and every one of those, the drive behind the mission concept is to answer certain fundamental questions. Let's take one. Saturn probe mission. One of the first things you have to understand is what are the questions they're trying to answer? How deeply into the atmosphere do they have to go? In fact, what you should want to do, if you're associated with that mission, is draw yourself a picture. This is the depth in bars up here, okay? What is the science value of the mission as a function of how deep you get into the atmosphere? In other words, if you wanted to imagine this, what's the partial derivative of the science value with respect to the depth? Where's the inflection point? If you get to 10 bars and no new questions can be answered until you get to 150 bars, that tells you an awful lot. You don't want to spend the time and effort to do that. We'll go to another one, a Venus surface sample mission, where somebody's trying to find out what's going on chemically or mineralogically on the surface of Venus. Maybe the key thing is that you want to understand the difference between what you get from remote sensing instruments, contact instruments, and actually obtaining a sample. In all those cases, you have to go to the scientist. You have to say, what are the questions that I need to answer both what I am doing? So that's number one, science smart. You see, and I fouled up because I need to write all these 10 on a sheet of paper, because somebody told me that when it's all done, they need to have one sheet of paper on which all 10 are written. You know how people are. So I'm going to do that over here, and I'll use the rest of the thing. Science smart. Okay. Number two. Now, somebody asked me, are you going to do these in priority order? And I said, no, they'll be sort of in a fuzzy, quasi-priority order, because I like to talk about things that, contiguous, go from subject one to subject two. There are more or less. This is definitely number one. Now, nobody's going to be surprised about the next one, except that I'm going to include things I haven't included in the past. Knows all the partials. Now, I've laughingly said many times, system engineer has to know the partial derivative of everything with respect to everything. But most people thought that meant engineering-wise. If you're on the front end of this thing, you have to know the partials with respect to such things as cost. Oh my goodness. Another person comes into my office and I thought I was going to be an engineer. And here I am, I'm spinning up. Please turn off your cell phones, it's rude. Okay, now here I'm spending all my time trying to figure out how much something costs. I said, well, I'm sorry, but that's what you got. That's what we have to do. Now, there are many engineers who can figure out the partial derivative of the design of the C and DH to how fast things work. That's not what I'm talking about. I'm talking about really big things. Somewhere in the mind of this front-end systems engineer is a rack-up of the prioritized questions that they want to answer, and if he or she is really clever, like Tom Spilker, they know what it costs to answer each one of those questions. So that when Ferouz, or somebody who's walking around worrying about selling the thing, comes in and says, okay, all I have, I'm sure this will never happen to you in your career, I only have $216 million for this job. You have to go, okay, let's see, we can answer 1, 2, 6. Can't answer 3, 4, and things like that. That's what you need to know. And is it fun? This depends on what kind of an engineer you are. Remember that statement I made about intellectual curiosity? There's all kinds of challenges. Now, I have 7 sons, and some of them operate freeform. My oldest boy is an entrepreneur with a capital E and lives in some domain that I have not yet found. Okay. I have another one of my sons likes to be in a nice circumscribed arena. When you talk to him, he's trying to figure out, okay, are you giving me a lecture? Yeah, that's important. Not what I'm saying. It's important what box we're in. So engineers fall into the same category. You have to realize that should be part of your intellectual curiosity to try to figure out what all these partials are up front. For example, you need to understand the panache coefficient of the mission you're dealing with. What? The panache coefficient is roughly defined as the degree to which an ordinary intelligent person, I used to say just ordinary people, and then I realized they're all watching reality shows. So now I say an ordinary intelligent person, okay? What will be the reaction of this ordinary intelligent person? Panache is style, whether or not it moves people. There are some missions, unfortunately, which suffer from a lack of panache. Now, I was told not to say anything bad about anybody today and to adopt a modified thumper policy. You all know what a modified thumper policy is in Bambi, okay? You remember when the rabbit's talking to the skunk, and up comes the mom, and the final outcome of this interaction is that if you can't say something nice, don't say nothing at all. Okay, that's a thumper policy. A modified thumper policy is if you can't say something nice or at least neutral, then don't say anything at all. So I am not going to call any particular mission. I'm not going to cite a mission that has a low panache coefficient, but I want you to imagine in your mind some mission that only the cognoscenti can appreciate and cannot be translated in any way to a normal human being so that they get any. That's a hard mission to sell. If you're the front-end systems engineer on that mission, you should be spending your time in bars. No, listen to me, seriously, trying to explain to the person on the stool next to you why they should give a bleep about that particular mission. You have to practice it over and over and over. Now, I have noticed that panache coefficients naturally go up, directly proportional to the intake of alcohol. I'm not sure whether or not this is due to the speaker or to the receiver, but that's number 2. All right. Number 3, an active corpus callosum. Okay? Now, another way of looking at this, because people said that I can't do that, is to put what appears to be an oxymoron up. A visionary skeptic. What? I want you to think about that for a minute. A little bit about the organization of the brain. A corpus callosum is the great network piece of structure in your brain that attaches the left brain and the right brain. For those of you who aren't into brain mapping, let me tell you a little bit about the 2 sides of the brain. The left brain is mathematical, logical, deductive. Most of you in this audience have very active left brains, okay? The right brain is aesthetic, intuitive, and inductive. It is said, and I refuse to accept these gender-specific studies, that women are better able to multitask because their right brain's communication with their left brain operates in parallel systems rather than in serial systems like the brains of men. I will not make any more comment on that. It is just to let you know that if you're going to be a systems engineer at the beginning of this activity, you have to have this particular, one of my sons said, this is schizophrenic, Dad. No, I said, it's not schizophrenic. They don't both dominate at the same moment. They just have to communicate with each other. Sometimes it is necessary to have the intuitive burst, the vision immediately pass over to the skeptic to say, but that's not possible. Now, there are people who get upset with me when I cite specifics, but once upon a time, a very, very nice young system engineer walked into my office and told me, pronounced to me, that a Venus surface sample return would only cost about $6 billion. I said, you want to go outside and come in again? I said, there are a few problems associated with that. And this person then began to lay out for me all the magical things we could do with a Venus surface sample return. The person was really in his right brain, okay? There was nothing there about, and by the way, all we have to do is land a launch vehicle that can rise up through 100 atmospheres of pressure on a surface that's 400 degrees centigrade and stay there for long enough that we get something useful in the way of a sample. And when I pointed it out to him, he said, good point. So what you have to do is you have to make sure these two are connected. Next characteristic, a nearly infinite initiative coefficient. What in the world do I mean? Initiative. You can spell it. Okay? This person should be like a Tasmanian devil. This person should never need anyone to tell him or her what to do today. You don't come in at 8 o'clock and say, I wonder what my boss wants to do today. There's a list of things. Now, I sometimes praise people, and that's okay. I want to tell you that this characteristic is embodied perfectly in Leon Alkali. If any of you know him, there is nothing he ever needs to ask anybody before he knows what to do. He's out there. He's doing what he's supposed to do, and these people commit sins of commission, never sins of omission. I don't want somebody up here who's worried about committing sins and therefore just go and commit like crazy. This is not an easy attribute for people to deal with. One of the things, I talked about this with another young engineer who came into my office, and he said, but my boss doesn't want me to do that. Then I said, your boss is in the wrong job. I said, you want me to tell him? No, I said, I will. and that's true. If you're on the front end and you're a boss, if you constrain your people, you're nuts, okay? You aren't going to get the job done. So somewhere along the way, I may be asked to give a talk about what characteristics should you have to be a boss. But unfortunately, I'm not sure I could do such a job without a lot of humor. Okay, has project experience. Oh my goodness. Had a lovely young lady in my office, PhD, and I don't want to identify, just had a PhD and has worked for 6 years on what I call pie in the sky activities. Now, a pie in the sky activity is one that ends up with a paper product. It can either be something that's published in a journal, and I am not against people publishing things in journals, so don't deduce that from it. But there is a difference between someone who produces something that is on paper and someone who produces something that goes to another planet. Okay? One big difference is a big dose of reality. Okay? Now, this particular lady that I was speaking to envisioned a complete career for herself in paperwork. No, that sounds pejorative. In pre-phase A mission design and things like that. And she said to me, after telling me what her goal was in life, what do you recommend for me to do? I said, go get in an ATLO activity. She said, what? I said, yes. I said, I think it's time for you to go and sit on the floor where the spacecraft is being tested, watch the procedures count. She said, that's boring. I said, okay. If that's boring, then how do you pretend to believe that you can design something that must go through that particular piece before it gets to the end? So now I have a big statement to make. Tom Gavin's mantra is everybody has to work on both flight projects and in central line organizations. I got another one for you. Everybody should work all different phases of the mission at some time in his or her career if you aspire to lead roles as systems engineers anywhere. So, if you're going to put a systems engineer on a front-end formulation project, you need to make sure that that lead engineer at least has this dose of reality, some real experience, like poor Kevin who had to work 99 hours a week for 16 or 18 weeks in a row. He'd be a good candidate now to do this sort of work. If you don't have that, then you don't have the leavening that's necessary in order to make sure that stuff is being done in a reasonable way. Okay, what's next? A consummate juggler. Consummate has 2 M's, I know that, okay? Juggler has 2 G's. And another way I'm going to put this one is comfortable with chaos and options. All right, another story, great story. One of my favorite young systems engineers who was working on a pre-phase A, and he came in and said, I am so tired. Yesterday the baseline was this. Last week the baseline was this. The week before that the baseline was this. What am I supposed to engineer? I said, you're supposed to be engineering the options. He said, what? You're supposed to be able to handle dealing with all those things simultaneously. You want an amazing options hornet's nest to get into? Our leader, at SMD, has now decided the next flagship mission at Mars is going to be a sample return. There are only 100, maybe more, different ways you can do that job. Okay? And it's options. Got to juggle, got to juggle. And you can't worry about the fact that things may change and may change radically at any given moment. So you keep your information base in very soft cells so that they can move from place to place without any difficulty whatsoever. Now, this particular characteristic is one that people who like their lives circumscribed cannot deal with. I have had people who I thought were brilliant engineers, and I've moved them to the front end of tasks, and they have come apart at the seams because they keep asking questions like, how do I know where I'm going? I said, well, that's part of it. It's the journey that's part of the process of defining the whole thing. So that's 6. Next one is, oh, I forgot to put the word separates up here for those of you taking notes. It separates the wheat from the chaff. Boy, is this one important. This is important in your daily life as a front-end engineer. You have to understand what is important. There's no way you can do the whole job. You have this much money to do everything you're supposed to do. You better figure out what's important. Prioritize. Schedule your time. Funny story. A friend of mine working on a proposal. I'm coming into his office after he's had a meeting. Out of curiosity, I'm curious, all of you know that. So what was that meeting about? And he told me. I said, why in the world did you have that meeting? He said it was on Meeting Maker. I said, but the partial derivative of your work with respect to that meeting is 10 balls won. He said, I never thought of it that way. I said, if you don't manage your life that way when you're on the front end, you're wasting it. Now, project managers on the front end have to also sit very carefully and say, okay, what is important for me to spend my money on, and what do I not have to worry about at all? And this is very important and leads to the next one. Multidimensional risk analyst. Okay, I know. It's a long word, risk. It might not fit on the page. All right. There are 3 major domains of risk that the formulation systems engineer has to keep in mind at all times. The first one is the risk that the mission will never occur. Okay? Now, if there is something that is not important for the other risks, but is important for the mission perhaps never occurring, you better pay attention to that one. I have issued the controversial statement to my colleagues in the Mars program that I do not believe there exists a human being who could take the job as head of SMD and embark on a Mars sample return mission when the only payoff from the whole thing is when the sample comes back in 3.5 years. And if somebody better figure out either how to soften the world, because when it comes down to it, somebody's going to have to say, I've got whatever the number of billions is. Let's say $4 billion is what I'm going to do. You've got to at least figure out how to make the probability of success, when you multiply all these probabilities together, high enough that somebody can believe. It's not about the science. You understand what I'm saying? Everybody knows. The decadal surveys, I did my first Mars sample return study in 1979. Okay? And then it was just right on the horizon. But somebody is going to have to stand up and say, we will spend $4 billion for something that is worth 0 until the sample comes back to the Earth. That's going to take a very large person. There are other risks. Remember I was talking about the panache coefficient? It doesn't matter how good a design you have, how low you can make the risk in anywhere else. If nobody's interested in what you're doing, if the guy on the bar still next to you has fallen asleep while you were describing the magnetic field of Humpty Dump, okay, then you know that you're not getting anywhere with that particular one. So that's one domain, right? The risk that the mission will never manifest itself. Risk number 2, the risk that you cannot deliver it on time. That's the development risk. Okay? In order to do this job right, the systems engineer has to have in his mind or her mind at all times a list of all the things that are brand new associated with this spacecraft or mission or whatever it is, a list of things that have been maybe done once, a list of the things that are old hat, and must realize that everybody who uses the word heritage means something different. Okay? I inherited part of my brain from a lizard. True. The brain has 3 parts. The reptilian part, overlaid by the primate part, overlaid by the human part. It is true. And I can well imagine reading in a proposal to make me that someone would write, and we have inheritance and heritage from the reptiles, which you know were successful for 400 million years. Therefore, we should go forward. Okay, that's the second dimension. The third dimension of risk is mission risk. Now, I realize that for a long time, Tom Gavin has believed that the mission ends at launch. Okay. Nevertheless, there are a few real problems associated with flying these complicated spacecraft. Just last week, I was sitting down with some of my contemporaries on one of our leading projects, discussing with them how it happened that the solar arrays struck the spacecraft. Okay? Now, these things happen. I'm not throwing stones at anybody. But the whole point is, if you have minimized, if you've gotten the thing sold and you've gotten to the launch pad, but the risks of being able to do the mission are too great, you have failed just as much. So this all has to be taken into account. And the way it has to manifest itself is through an orderly risk reduction process, which needs to be part of every pre-phase activity. It should go like this. Where are my Achilles heels? Now, I realize Achilles only had one heel that was vulnerable. Give me a break. Okay, where are my Achilles heels? At what is the pace with which I solve the problems associated with that? How do I convince others that I've taken care of it? So that's what I mean by multidimensional risk analysis. Next one, a master of margins and reserves. And in this, I mean, I have to tell you another funny story. Another office session. Someone comes in and says, doing this formulation work, and I'm looking at their cost statement. Okay, it has 4 significant figures. I say, what in the world is this? Oh, it's 1762. 1762. And what is the uncertainty, would you say, in that 1762? He says, plus or minus 300. So why do you put 62? point here is that if you're on the front end, you can't be one of these people who likes to write a bunch of numbers. You have to realize it's okay to get the first two. Farouz will take that. Farouz can handle it. The range, first two, that's all he cares about. If you know the first two and they're close enough and how far they can be off. But let me talk to you about a margin that has not been discussed as well. All of us know about mass margin, power margin, schedule margin, that sort of thing. But let me talk to you about another margin. I call it science margin. Let's presume, and Bob Pappalardo, I hope you don't mind if I pick on you, that in order to meet his requirements for Europa orbiter mission, you come up with, if I get up to here, I can do all the things he's asking for. And we went through this process that I was talking about earlier, the why to the what, and so on. Now, the mission should start with and have a knowledge of how much margin there is above and beyond the requirements to meet the quality of the scientific inferences. If I had to say one spot in which our system engineers fall down in pre-phase A, is they do the margin with respect to the mass, they do the margin with respect to the power, but they do not think about establishing a structure in the beginning where if it is achieved, it goes beyond, by some quantifiable amount, the goals of the science community. That is the only thing you have to trade as things go downstream, that you can actually say, that to keep the costs down or whatever else. If you start out with no margin, and if, I'm not going to do something silly here, if I had colors of it, if the quality of scientific inferences drops off precipitously when you drop, then you do not have a viable mission. I've talked to Farouz about this. I'm trying to figure out how we implant a methodology to do this, because we do the mass, we do the power, but we don't do this very well at all. And so it's a standard question that I ask everybody who's got a proposal. How much science margin do you have? The other thing has to do with reserves. It is almost always true that when I ask, upon what are your reserve allocations based, I get one of two answers. First, someone quotes the Bible. You think I'm kidding? We have now enshrined on tablets, like Moses. We've gone to the top of the hill, and the design principles and the flight project practices have come down upon us. For goodness sakes, if you aren't smart enough to figure out that those things are nothing more than don't forget to think about this possibility, you shouldn't be in this game. Okay? So that's one thing. You've got to be able to realize that those margins and reserves that are suggested there are for a generic mission. If you have new things, particularly new science instruments, that the only way you have estimated their costs is by putting them in a model that uses only their mass and power, some of you are looking at me as if such a thing would never happen. We have people, I have had someone in my office say, Nickum says, and I say, Nickum, kickum. What are you talking about? Okay, trying to make a point here. You have to know what kind of reserves to apply, and they should be based on the maturity of the concept at the time you're doing it. Ah, now here we go again. Watch this one. Components 1 through 77 all have heritage. Chart 6.3 shows the heritage of parts 1 through 77. The paragraph that's not written is, of course, they've never been put together before, and if you try to put them in a box this size, they'll explode. We need to understand about those things. Number 10 understands the complete toolkit. What in the world am I talking about? Oh, there's a toolkit. And what does this toolkit consist of? A whole bunch of models. okay? And they're hysterically funny. I mean, if you get into the guts of them, I mean, some of them are such things as, well, the transport model for, I had this following conversation. I was trying to work with the Europa Orbiter people on the radiation design for their mission. And so I had the temerity to ask questions below the surface level and to try to figure out what these computations were really based upon. Here, following the suit. I'm not casting aspersions on anyone, just want to tell you how I went. Okay. The transport model of determining X, Y, and Z is used widely in the industry for determining the amount of ionizing dose that comes into such. I said, okay, is it a conservative model? Well, we don't know. Well, why is it we don't know that? Well, we didn't develop the program. Okay, fine, I understand that. Who developed the program? Well, we don't know that either. But it was somebody at such and such a place in 1904, not really, but I said, well, how do you know when you do this and you use this model that it applies to the problem that you're talking about? We don't have any other model. And this is the kind of thing. You have a whole bunch of tools. You have cost tools. You have simulation tools. And the person on top of all this who's doing the system engineering up front has to understand the strengths, the limitations, the range of those tools. Sometimes we get real breakthroughs. Like, I was so pleased when I was looking at the Jupiter Science Orbiter proposal or report or whatever it was, that there's a new kind of trajectory somebody had come up with called a ball of yarn that operates in a specific region in the restricted three-body problem. Somebody spent some time saying, what tools do I have to try to make a better orbit around Ganymede and get what I want to know? Other places, we are woefully lacking in tools. For example, I've said this over and over to Ferouz and everybody else. We are not even here on the curve where with propulsion missions we're up here on understanding the mission analysis trades associated with continuous thrusting missions. We don't have the facilities with the tools and others. That all needs to be in there. And the upfront system engineer has got to milk all those things to try to go to effect closure all the way back to achieving the science in the best way they can for the most effective cost. Now, why am I giving this lecture? Because the world for JPL has changed. Once upon a time, oh, my kids love it. When I start a story, once upon a time, they just all go, oh boy, and here comes something. Once upon a time, there was a place called the Jet Propulsion Laboratory, okay, which was assigned work to do because of the worldwide recognition of its fundamental uniqueness and competence. And therefore, all one had to do was wear one's JPL badge, stride in the door, and ask what work was arriving today. Folks, that's not where we are anymore. We are in a world of competition. And I'm not going to, use the metaphor of the sharks are out there, but hello, if you're walking in like this, what work are we going to do today? But you don't want to lift your finger to help get into new work. You know what's going to happen? Someday there won't be any door for you to walk into. Because of our past history, it has been established at the Jet Propulsion Laboratory that the most, I'm trying to figure out the exact words, that the quickest way to get to the top and to be recognized is to be a flight project weenie, a hero. You solve some fantastic problems, you manage something, and you just shoot right up. Okay? And that if you do anything associated with technology, or for goodness sakes, that stuff that goes on in the front that we have to correct after the people send in all the proposals, you're going nowhere. That time has changed. If we don't get some of our clever people who have these characteristics up front, working to solve the problem of getting the job in the first place, this tremendous institution of great historical import will be a closed chapter in a book covering about 50 to 60 years. I don't want that to happen. I want those of you who still have 20, 25 years in your career left to ask yourself the question, do I have what it takes to do the job in the front end as well as on a flight project? Am I willing to recognize that sooner or later the Jet Propulsion Laboratory will reward those people as well as they reward those who work on flight projects? And if you answer that question correctly, then Firuz and his team can have the staff they need to bring the same competence and the same outstanding characteristics to our formulation work that we have in our flight work. Let me make sure you all realize, I think this is the best and brightest group of people I have ever seen in my life. I said when I was asked why I came back to do this work again, I said 2 reasons. What you do and with whom you do it. It's intelligence and integrity. But we are threatened right now. We need to spread out, get some good folks up front. Anyway, thank you all. Had a good time.
All right. That's my second or third time watching that. And every time I watch it, each time I manage to get something different out of it. It was a really good video. So we're going to shift over to the panel discussion. Let me just bring up my questions and a quick nod from Steve, Dan, and Dave. You guys are ready? Okay, thumbs up, thumbs up. All right, so let me start with a question. Which one of the 10 characteristics most resonated with you and why? Start with Steve.
All right, cool. The first one was absolutely the one that resonated. Now, I understand that the speaker is dealing with space projects. And so his version of Science Smart, understanding the science, we can translate that for those of us that are not involved in science or space missions. We can translate that to understand the operations. And one advantage I had when I was young and just entering the field is that I had the opportunity to talk with operators. I went out, I was able to go out into the field, talk with the operators who were using either old versions of systems or they were not able to do what they needed to do. And they told me in their own language. And I was able to see what their problems were or what questions they were asking. So that really resonated with me because at a very early age in my 20s, I realized how important it was to understand the problems that the people on the ground, if you will, are facing.
Yeah.
And so in science missions, yes, it might be talking to the scientists, and I understand in space missions, the science is the driver. In non-space missions, the operators are the driver and what they're trying to get done. So I was really excited to hear what he had to say. What are the questions that need to be answered from the people who need to do the job?
Great. How about you, Dan?
Yeah, I had the same response, and my quick background in systems engineering is I didn't speak the same language as you guys 4 years or 5 years ago. I came from industrial systems engineering in 1993 through the Walt Disney Company making theme parks. And what I learned through the experience of conceptual design of theme parks was you really have to get in the head of the people who run the rides and ride the rides. Then you can make a system model that makes sense. And as I got to APL into systems engineering and in COSI more specifically, we boiled that down. I think the kind of people who think like this, as long as we're willing to first go listen to those people and go more than halfway across the street to whatever field it is that we're supposed to be learning about.
Okay. How about you, Dave? Another vote for number one, or you got your own vote?
So I did have it where it was listed on here, but I'll go differently than what Steve and Dan had. So I think it was between number 2 and number 5. So it was knowing all the partials and being the consummate juggler. And I say that they're kind of related because in the beginning of the conceptual design, the being a generalist, being that multidisciplinary generalist, and also juggling a lot of different projects. So where Steve and I work, we're doing a lot of projects, and it's that cross fertilization of different ideas from different projects, and it's amazing how you can solve one problem here, and you can take that exact same approach to a different project literally across the hall or a different building, and it's like you just like created fire or something, like you were like awesome, and you solved the whole world's problems. I'm like, not really, these other guys did also, but it's the whole different types of ideas to be able to then come up with either a novel approach or a amalgamation of different approaches to address that.
Great. And this is a small group, so why don't I throw that question open to anybody else who'd like to answer it? We got a nice intimate crowd here tonight. Anybody else have a one that resonated with them and why, and something clicked that you'd like to share? That's okay. Everybody's a little shy. That's all right. We'll get into it.
I can go ahead.
Yeah, go ahead, please. Yeah.
The comment, like only I got grasp on that lady with the PhD, because I'm doing a PhD as well at George Mason. So yeah, and that's true. Like everything that we did, it's only on paper, where he mentioned, yeah, you need to have something realistic. So this is like something really important in system engineering field. Because usually the student, they came up and they start like asking questions. Especially I'm doing my thesis on MBSE and system architecture. They say, what's the reason you're doing all these diagrams and using DODAP, UF? Is there any benefits? And sometimes, yeah, even the professor, they can't explain it well.
Interesting. No, it's a really interesting point of view. So the thing about project experience resonated with you because you felt that pain of sort of speaking academically, right? The academic answer, you don't know how that necessarily translates into the quote unquote real world. Is that it?
Yep, into like practical things.
Yeah, I guess the one thing he didn't mention is that, yes, we highly recommend getting project experience, but they don't mention that you may not survive the experience, right?
Yeah.
Because those are real scars on people's backs that they then learn from.
Mm-hmm.
Okay. Let me ask this, Dave, since we ended with you, I'll start with you. The talk was around NASA space missions, and that was where most of the examples came from. Did anything kind of occur to you where you said, oh yeah, I could have applied that idea to this problem? And maybe Dan will say, it did, like Dan was sort of touching on ride design. How about you? Did you see an other areas that this could apply to now?
There were, yes. Since I don't work at space projects where we work, but other either defense or Department of Homeland Security, yes, these definitely applied to all the different lessons. I like the one about the reserves and the margin, and because it's always like what we've been taught in school, and here's your margin, and here's you got to have a margin reserve and all of that good stuff. The thing that he said about you have it to trade, and I've seen that, I think, in the literature, in some of the stories in the news on how they're trading a lot of that and making the decisions, and that's that good tangible attribute to then be able to actually get the project off the ground and into the field.
How about you, Steve?
Yeah, I resonated with the risk and saw how that is huge in any domain, not just the mission. I get with space science, obviously, if risks are realized, then the entire mission can fail. So it's much more of a catastrophic type of risks that we generally deal with. But even in what I'll say non-space engineering, whether it's Homeland Security or defense or the commercial world, understanding the risks is absolutely critical. And I've noticed that risk management and risk engineering is a skill that not many people have. Unfortunately, everyone thinks they have it. And that really becomes an issue, because risk at its fundamental level is very simple, right? Likelihood and consequences. And yeah, we can understand that, and we're going to mitigate it. But when I actually get into risk analysis with other engineers, I find that there are nuances of, and especially in what Gentry said, multi-dimensional risk, how the idea of one risk is not independent from all the others, that there's a great deal of interdependency or dependencies among those risks. And yeah, you can mitigate any one of them, but what happens if two risks are realized, or one risk is realized and that increases the likelihood of another risk, and how are they all tied together? So that's something that I really believe systems engineering could help with. And then maybe that's a thrust area that we can explore.
Okay. Dan, do you want to weigh in on that one?
Yeah, I was going to throw in number 11. And comment on the number 11, which
Okay.
down at the bottom, he said what it really comes down to and why he returned, because I presume he had left for a while and came back, is what you do and who you do it with. And one of the things that I think we should do as systems engineers is, what is the elevator pitch to businesses, industries, entrepreneurs, particularly as relates to things like AI? I mean, everybody's got an AI engine that's going to work. Well, I honestly believe that system engineering applied to AI could be a secret sauce, but we got to be able to talk about it, what it is, what we do, and how we do it, and who we do it with. And it's not about the behind the scenes training algorithm. It's the rest of what we do. So what we do and who we do it with. How do we get to a concise way to say that?
Good point. Mr. Campbell, I want to pull you in. Do you have a question or a comment, anything?
I was thinking about some of the juggling that he was talking about, how things are always changing. And yeah, that there needs to be, we all know about agile development and so forth, but there's some things like scope creep or going beyond scope creep that happens where they just completely change everything. I don't quite see how one is able to balance all of that out. Does that make sense?
I think so. I think he wasn't trying to claim that any of these things were easy to do. When he said be a consummate juggler and move between chaos and options, he didn't say that that was necessarily going to be easy to do, right? And he didn't give any hard and fast rules on how to do it. He just said it needs to get done.
Mhm.
So I think your observation is spot on. I mean, that is one of the things that's got to be addressed.
And Mike, let me add on to that, because I just recently came from a project where we were doing medical research for military medicine. And the idea of being comfortable with chaos, it is so important. And this really separates systems engineers from traditional or design engineers, where traditional engineers, they like to start with a common or a very good set of requirements that doesn't change, that is very, very stable. And then you go in and they will put together a design for you. Systems engineering is not that way at all. And I really like how the speaker talked about part of systems engineering is having options, so that when things do change, and they will, you are prepared as the systems engineer. You understand, okay, if you're going to make a change in this area of the system, then I've already at least considered that, and I can give you some impacts. Which, by the way, is also a reason, or an underlying fundamental reason why we do architecting. So that when there is a change in the system, I can put that change into my architecture. And if my architecture is formulated correctly, it will tell me all the different impacts of all the subsystems and external connections and my interfaces and my integration scheme, etc. And that really tends to be the strength of systems architecting or early systems engineering, which is what the topic was.
You know, I'm really glad you brought that up, because that brings me to one of my questions, which is that idea of, well, if we think of systems engineering when the canvas is blank as a type of systems engineering, is it really, right? Because you just said early stage system engineering, or really, are we really talking about systems architecting, which is distinct from systems engineering, in which case the talk could be retitled System Architecting as Usual, as opposed to this is a special type of system engineering. Dave, what do you think about that comment?
Yeah, so I go back to what Steve said at the very first time, and it was getting embedded in the field with the operators and seeing what goes on. And that's how I have seen systems architecting done right, is that you're actually going to the field, you're seeing what's going on, and then you're translating that into the actual artifacts for the system engineers. It'd be a radically different artifact if you didn't go to the field and you had no idea and you just read some books. You know, you're smart enough, but then it's not the same as you're getting that information, that feeling, like he calls it the panache factor, kind of like related to that, and that whole buy-in. If you're able to successfully get that buy-in to translate what you see in the field into the system engineering world, I think you've won really, really well there.
Okay. Hey, Clinton, I'm going to put you on the spot. What do you think about that architecting versus engineering distinction, or not?
I think there is distinction there. And actually, as you were discussing that, I was thinking it was bringing to my mind questions that I've been asked, usually by like people in so what do I want to say, domains that, on a project, different domains that are supporting the development of the system or whatever. And that question is often like, what's the value of a system engineer on this project? I don't know if other people run into that occasionally, but hopefully it's not your project manager. But
it's usually not stated that personally, but okay, go ahead.
Right. But you know what? When I thought about that, and to me, like the elevator answer is risk mitigation. That's the value that a systems engineer, ultimately, that's what you're paying him or her for, is to lower the risk in delivering this system through all the various things that they're doing across the whole life cycle of the project, So that was the thoughts that were coming.
No, that's good. Excellent point. Anybody else want to weigh in on the architecture versus engineering?
Let me party on to Clinton's comment, because I love that. But I'd also add the end opportunity, because one of the things that I've found in successful system engineering, and Steve and some friends of yours and some folks over here in FPS have done a lot of really good work. If done right, the operators at some point say, I never would have thought of that, or we would not have gotten that done quite as fast if you had not been here. Because we were all worried about the big elephant over there, and you got my risk tolerance down to, yes, there's an elephant in the room. It will be there when we're done. But if we can all see that, and I'm actually talking about Project Warp Speed to kind of context my APL work, we're not worried about that. We could do this. So I'd add to your risk opportunity, Clinton. And I really think you nailed what is our value proposition to folks.
And I think
risk to where they can believe it, and then show them a way to propel. It's always easy to use these space projects because, it's got launching and Saturn and all these other cool, rocket terms. But anyway, I just wanted to add opportunity to your risk thing, Clinton. I really like
And I think you answered, started to answer something Ahmed brought up earlier around, what do you say to people when they say, well, I see what you're doing with all this stuff, but what's the point of it all? And if you say to them risk mitigation, then the piece that when you can say that with years of real world experience, right? That's the answer. That'd be one of the answers that you might give someone as an example, Ahmed.
Yeah, I got it.
Any other, I guess I was going to ask a tough question, but let me open it up for somebody. Anybody else have any other thoughts or comments?
I just have one, and actually it came into my head when Ahmed, you were talking about your dissertation work with model-based systems engineering. From my observation only, and I'm very limited, obviously, but from my observation, I think we do a good job of model-based systems architecting and a poor job of model-based systems engineering. That's been my assessment for the past couple of years now. Our tools, I mean, pick your favorite, Cameo, Core, you name it. There's a whole bunch of them out there. Almost all of them are strictly in the architecture component. And how that has to ultimately interface or transition to design is a huge gap, I believe. Now, some companies and some organizations, some manufacturers and tool developers are starting to focus on that, which is exciting. But I think overall as an industry, as a community, we do very well model-based systems architecting and very poor model-based systems engineering. So when you get further into your dissertation, Ahmed, I would love to hear about it. So maybe you're a monthly speaker in the future.
Yeah,
because I really would like to hear about some of the outcome and output of your dissertation work.
yeah, me too. I was going to say the same thing. I would love to see a draft of your thesis or your thesis statement, whatever it is. I'd love to hear more about it myself. I think, I'm allowed to say something and break out a moderator role for a second there. I'm okay with MBSA, model-based systems architecting. I think that's profound. I think that's what it's always been. And I think that's what's been needed. I think the problem we've been doing is we've been trying to jam that round peg into a square hole. We should say, look, this is the architecting piece you've always needed and live there for a bit. So let me ask you guys the hard question. It wasn't in my list. So yeah. Oh, this is a good one. Did he miss anything? And I'll kick it off. I thought he had, but then I thought he missed what wasn't margins? I thought he missed I think it was the partials. Yeah. Like after watching it the first time, I thought he missed something around I thought he missed something that he actually did cover with the partials. So I couldn't come up with anything. I was trying to think, okay, what other characteristic, what quality, what lesson did he miss? Anybody got something?
Well, let me put in a plug for Dave. Only because Dave is like the guy responsible for conceptual systems engineering. I mean, he teaches it, he knows it, he talks about it. So when I have a question related to conceptual stuff, I go to Dave. So let me just pass it over to Dave.
There you
He's
go.
the expert.
There you go, Dave. What did he miss?
Yeah. So the one thing that I think he didn't have was socialization of and the continual feedback. So we do this a bit, and I'm going through this with a couple of newer projects right now, and we're going crazy within our own group, our team, trying to figure out like, what do they want? How are they going to do this? How do we get this right? And I'm like, you just got to put it enough, have it good enough to then present that and talk intelligently about it, and then get the feedback and learn together with the sponsors, with the customers, and get those different ideas, different perspectives, and they don't know all the answers either. That's presumably why they contract out to us to do some work, or anyone else. And then it's that back and forth. You could call it agile, you could call it spiral, you could call it iterative. But yeah, definitely you feedback and you riff off each other and you get the different ideas, and you can do that so quickly inside that decision loop than just kind of, you know, wringing your hands in isolation, and then, you know, hopefully you get there a lot later. So that's what I would say
So,
that he
so
didn't have.
would I reframe that as collaborative, as the
Right.
quality? Because
Yes.
what I think you're saying is that all that stuff you need to do, you can't just sort of say, well, my job is to take what you told me, your question,
Right.
make sure I answer, and then go off and do the answer. No, you're supposed to work together with everyone to move everyone. Great. That's
Yep,
that's a great, terrific. I'm with you.
Yeah. And let me just add to that. It's not just, you know, it's what I want to say is understanding it is one thing, but actually being comfortable doing it is another thing.
Yeah.
And so what I find is like, it's easier. Some people have it easier, you know, some people are more social naturally than others, or more engaging than others. But like, as you mature, you find out and you get involved in projects, more and more projects, that is a necessity. You have to be comfortable of getting in and discussing people knowledgeable in multiple domains, like he was saying about the partials aspect of it. He was saying you need knowledge in it, but also you're saying you don't always need the knowledge, but you do need to be able to ask the questions and be comfortable and engaging on that, you know, with others.
Great. Hey, look, I think that's a great statement to end on. It's 8 o'clock. I think we had a great meeting. It was different. I think you should talk it up with the people who didn't make it and say, hey, you missed some fun. And we'll be back to our regular format next month.
Yeah.
Any closing thoughts?
I really enjoyed this. I want to say it's like we haven't, at least the chapter hasn't done something like this in a while. And I think it was a really, I liked the ability to engage in discussion about topics more than, you know, just listening to a speaker the whole time. So I think it was a great evening, and it'd be nice to maybe do something in the future again, similar to this, like a panel discussion.